Welcome everybody. Hope you're enjoying our coffee break series so far. Thanks for joining us this afternoon or whatever time of day it is, wherever you are. Um, got a couple of introductions here to make real quick and start with myself. Some of you may have met me before. My name is Brandon Adkins. I'm one of the senior application engineers with the Quest integration team. And I'll be kicking off the discussion today with one of our special guests who I'll introduce in just a moment. We'll be talking about hardware for the software tools you need, and I'll be a bit more specific on kind of which categories we're going to cover, and then I'll let my guest really dive into the specifics on what you need for a combination of these tools. So quick little introduction on myself here too, if you want to get to know me a little bit. Like I said, I'm one of the senior application engineers. When I started with Quest, it'll be actually 10 years later this month. When I started 10 years ago, I really wanted to learn as much as I could about SolidWorks. I had used it in school at Eastern Washington University, where I got my mechanical engineering technology degree. I got to know SolidWorks there, and I wanted to continue learning more as much as I could, and Quest gave me a great opportunity to do that. That's my primary job, is I get to learn as much as I can about the software tools and even hardware tools that we offer these days to help our community around the Northwest implement those tools and learn as much as they can about it. So it's been a lot of fun for me getting those certifications and learning about products and so forth. A few other fun facts and personal stuff. I'm a Montana native. I grew up in Great Falls, born and raised there. I've called Spokane home for almost 20 years now, so I'm over in Washington now. You can see a couple of family pictures there too. I've got a almost 11-year-old daughter. You can see her there playing with SolidWorks apps for kids. And my wife and I out on Lake Coeur d'Alene last summer, I believe that was, taking a little jet ski ride. And then as far as personal interests, anything that gets me outside and active, maybe make an occasional batch of home brew, make some beer every now and then. You can see a little picture there of one of the hikes I did last year in Montana. A lot of fun there. I really enjoy doing that kind of stuff. So that's a little bit about me. Next, I will let my guest introduce himself. We've got William George from Puget Systems. Tell us a little bit about yourself, William.
Hi, well, thank you for the intro. I've been here with Puget for 14 years now, almost 15 actually. It'll be this October. I started in our production department. I was actually heading up that department when it was just a couple of us, um, and then moved over and spent 9 years in sales and consulting. And then the last 3 years, I've been in our labs department where I do testing on all the different software applications that we target for our, the folks we're selling systems to, which includes SolidWorks and other engineering applications, as well as photography, video editing, a handful of other sort of professional applications. I've been a computer nerd as far back as I can remember, since about age 4, when I first started using my dad's IBM PC, back when that's all it was, just called IBM Personal Computer. That was the model. And
Very
these
nice.
days, I still spend a lot of time on computers, but I'm also a husband and father of 3.
Excellent. Well, thank you for sharing, William. Like I said, we'll get to some more specifics on the hardware side of things. If you guys are not familiar with Puget Systems, they've been one of our partners throughout recent years for folks that are investing in new software tools. You need to be thinking about the hardware tools that go along with it. And we get those questions all the time in our support department. I've had a ton of those questions myself over the years. The rest of the engineers, I'm sure, would agree with me there that some guidance is necessary on this kind of stuff. Like William said, for professional applications, you really want to pair the right hardware tools with whatever it is you're using. So that's what we're going to cover today, is kind of some of those common questions. And where it all starts, I'm going to give you guys a sense of what are the primary groups of software users that we tend to get the most questions about. Obviously, within the SolidWorks family of products, there's a lot of different applications that potentially you could use. What are the ones we get the most questions about? We're going to cover some of that here today. So really what it comes down to is there's a few primary groups that I like to think about. So first one is going to be obviously your CAD focused user, who are the guys that are using SolidWorks assemblies, drawings, maybe doing a little bit of complex part design, or maybe they do some sheet metal work. Primarily just the 3D design aspect of using the SolidWorks CAD tool. That's the first group of users that we get the most questions about. Next, I would say, is the simulation focused user, right? If you're getting into the finite element analysis, computational fluid dynamics tools, or even the plastic injection molding simulation, we tend to get a lot of those questions to sort of follow up along with the CAD usage. The third one, I would say this has become more common in the last couple of years since we introduced the SOLIDWORKS Visualize tool, is for the photo rendering user. Now, this may also be a SOLIDWORKS user, but in a lot of cases it's not, and I'll talk more specifically on that, and then let William get into the tools that you need on the hardware side for everything we're discussing here. So for that CAD focused user, by far the most common question there, as far as what hardware to use for drawings, parts, and assemblies. Maybe you've got some relatively large assemblies that you need to deal with. As far as the software side of things, what tools are we using? It's primarily going to be the SOLIDWORKS 3D CAD, using those 3 file types that I mentioned before, but also maybe some of the add-ins, right? Maybe you get into routing, toolbox, CircuitWorks for collaboration with your electrical department. Maybe you're doing some sheet metal and weldment, or maybe mold design work. All those tools follow under the primary CAD umbrella, of course. Now, on the hardware side of things, we've got some main considerations to make. So the key here on this one for the CAD user, we'll cover what resources you need to ultimately do your work efficiently with SOLIDWORKS CAD. For the simulation user, this varies depending on the organization or the individual, but maybe they're not a heavy CAD user. Maybe they are. I would say around the Northwest, it's pretty common for a lot of CAD work to be done by the simulation user, but they're probably not detailing drawings and doing that kind of stuff, just mainly focused on the 3D operations. Now, as far as what software tools they might be using, I would say most commonly we get questions about the FEA software add-ins, but also you've got the computational fluid dynamics, like I mentioned, plastic simulation, and even some of the kinematic motion tools with SOLIDWORKS Motion. A lot of those recommendations that you'll need for this group of users kind of fall within the same range for most cases. The CFD tool, I think, is probably going to be the one that differs the most from the other ones. But keep some of the stuff that William's saying in mind for other applications, like when we're talking about FEA. A lot of those general recommendations will apply to a tool like SOLIDWORKS Plastics or maybe Motion. So on the hardware side of things, depending on if you're a heavy CAD user or not, for the simulation guy, what's going to be your best bang for the buck? And then on to photo rendering. This is really a non-CAD focus. Maybe you're a content creator for marketing or something similar. We tend to focus there on just reusing the CAD data and not actually creating it. However, when we create information using SOLIDWORKS Visualize, maybe it's a series of professional looking animations or product images, whatever I can create that's interesting and high quality. Obviously that takes a lot of horsepower to get there. So we do get a lot of questions about that these days, especially since SOLIDWORKS Visualize is a complementary product that a lot of you folks have access to now. If you own SOLIDWORKS Professional, you've got Visualize Standard included there. So specifically on that, what tasks or what resources do you need to actually do those tasks and create high quality output? So think about these 3 buckets of users as we're going through here, and William will make some recommendations on specific hardware. But really what it boils down to is each one of these are going to have kind of their own specific tool set as far as hardware goes to go along with the software. So I just wanted to introduce some of those ideas to you and the most common questions that we get along that front. The other thing I want you to keep in mind here too is I talked a little bit about this as we were going through. Sometimes the CAD user is the one that uses all of these applications. Also keep that in mind during the hardware recommendations, because what you may be able to invest in for your CAD workstation will also benefit for some of these other tools. Not only that though, maybe I want to use a different piece of hardware to do some of these other tasks. Like if I'm busy with CAD work and I want to offload a simulation, or offload a rendering. Maybe I consider having my workstation as maybe a little bit lighter duty, but then I've also got a simulation workstation where I offload some of that work to, for example. That's something that you may want to consider as we're talking about specific recommendations there. So that kind of covers it as far as the primary groups of users. So you guys will be thinking about those as we go through. Next, I think I'll go ahead and kick things over to William here. He'll be covering the best fit hardware for each of these different scenarios. So William, let's go ahead and switch over to you here real quick.
Thank you. And yeah, I'll go through those same three primary categories of users. Let's see. Get the screen share going here.
Excellent.
All right. Let's see. Oh, hang on a moment. Oh, sorry, it looks like webinar is not liking to share my screen. Just a sec. Sorry about this. Is it? All right, is that sharing properly, does it look like?
Yep, I can see your slide there.
Okay. All right, so for the CAD user, let's see. Sorry, I'm getting a weird message from the webinar. Is it showing for the CAD user CPU at this point? I'm just going to trust it's on the right thing.
It's looking at a slide that just says for the CAD user.
Okay, yeah, it's paused screen share for some reason. I apologize. Every time I try to tab over to the other window, it doesn't seem to like it. Okay, weird. Sorry. Okay, there we go. Let's see if, there, we got it going now?
Yep, looks good.
Okay, sorry about that. Okay, so my apologies there. For the CAD user group, that first group that was mentioned, modeling in SolidWorks is mostly single-threaded, and this actually applies to a lot of other engineering and modeling and design applications as well. So the main thing that matters is going to be clock speed on the processor. You don't need a lot of cores, although every single CPU these days is multi-core. It's been years and years since there were single-core processors. But anything around the neighborhood of 8 to 12 cores is going to be plenty. You can even get by with a few less than that. But the main exception to that is going to be if you do some of the photo rendering stuff, which we'll talk about a little bit later, but specifically the PhotoView 360 tool within SolidWorks does use multiple cores very well. I think that's somewhat antiquated nowadays, is my understanding. We still do some testing on it here because we have a few people that ask about it, but it seems like a lot more folks have gone over to visualize. So we'll be emphasizing that more when we get to the rendering section. Some examples of good processors are going to be stuff in the Intel Core i7 and i9 families, as well as the Ryzen 3rd Gen from AMD. And within each of those, you're going to want to focus on the top end models within each series. They tend to go from lower to higher clock speeds. And since that's the driving factor, you're going to want to, if possible at all within your budget, be on the higher end of those individual families. Some specific good examples, the Intel Core i7 9700K and 10700K, and the i9 9900K and 10900K. Those are the top end of those two families in the last two generations. And then on the AMD side, I wouldn't go any further back in their product line, but the latest gen, the 3rd gen Ryzen chips, which start with a 3 in the model name, those are quite good. And so the Ryzen 7 3700 and 3800X and the 3900X in the Ryzen 9 family are all fantastic for this. The primary thing that's going to be affected by the CPU within SolidWorks, or excuse me, by the GPU then, the video card, transitioning over to that, is how smooth manipulating parts and assemblies is going to be, zooming, rotating, etc. And what you want to look for first and foremost is something that's certified by default. If you don't use a video card that's actually certified, SolidWorks will recognize that and disable features like Real View, which can make a big difference in terms of the image quality when you're looking at stuff. Further, the more complex your assemblies are or parts, the more powerful a video card you'll want. And you can kind of see this. I think it might be a little bit small in the text, and I apologize for that. These are some graphs from our recent articles showing frame rates when rotating an assembly at two different sizes. One that's a car down at about 1.5 million triangles, and then a massive bridge assembly at 40 million triangles. And as you can see on the larger assembly, frame rates drop off much more steeply at the bottom end of the video cards that are out there. So the bigger your stuff is that you're working with, the more powerful video card you're going to want. And in addition to that, screen resolution also impacts things. Here's that same car assembly, but at both 1080p on the left and 4K on the right. And again, you can see the frame rates are impacted just by running at a higher resolution on your monitor and thus in SolidWorks. Further, any of the features you want to enable, like Real View, edges, ambient occlusion, any of those things within the viewport in SolidWorks, each add to the requirements on the video card. So you'll need something more powerful if you want to have all of those enabled versus if you just want to have, say, Real View only or just edges and stuff. Moving on from the video card then, RAM considerations. RAM is random access memory. That's the short-term memory in the computer. And that's where it's going to be storing everything that's active at any given time, which as soon as you boot the computer up, that's Windows. And that by itself these days needs nearly 4 gigs of memory. And then on top of that, SolidWorks itself is going to need 1 gig or more, depending on the size of your assemblies you're working with. The safe minimum these days is considered 16 gigabytes. And then if you're working with particularly large stuff, you might need to go even bigger, up potentially 32 gigs or whatnot. Plus, you're going to want to keep in mind any other applications you have running. I don't know about you, but I tend not to ever have just one thing going at a time. I've probably got about 6 or 7 applications running even right now just during a webinar. So you'll want to make sure that any other applications are also factored into the total memory you get. And then just some other considerations as far as hardware goes. These days, there's no reason not to get a fast solid state drive for at least your operating system, programs, which usually will be on the same drive, and then files, which you can keep on the same drive, or some people like to have multiple drives. But definitely those 3 things, at least, I strongly recommend having on solid state drives. They're vastly faster than traditional hard drives, and we've also actually found them to be more reliable as well. You also want to ensure the system is going to support the type of network you're going to be putting it on. Almost all computers have wired Ethernet ports, at least on the desktop side of things. That is not always the case with laptops. And then wireless, so if you're using Wi-Fi rather than a wired connection, you want to make sure that's supported as well. It can be added to systems through like a USB dongle, but those are notoriously unreliable. So I'd strongly recommend out of the gate with the internal hardware, you make sure it's going to have the right network for you. And in particular, if you're going to be on a wired network, make sure it supports the right speed that your infrastructure is. If you've got a 10 gig network in your office and you only have a 1 gig Ethernet port in your system, you're not going to be getting the full potential when you're transferring files or sharing things around. And then if you're using multiple monitors, which I do at least at work. At home, I only have one, but at work, I've got a couple. You want to make sure that you've got the right number and type of video outputs from the card in the system. These days, if you're going with a Quadro card for SolidWorks certification support, most of those only have DisplayPort outputs, which is a newer type of connection, and most newer monitors have that. But if you're reusing older monitors, you're going to want to take a look at what inputs they support, and you might need to pick up some additional adapters from DisplayPort to DVI or HDMI. And just to give kind of an example of, summary of what all that would look like in a system, one of the most common configurations we're selling these days for SolidWorks is an Intel Core i9 9900K. I mentioned the 10900K, but those literally just came out a week or so ago. So there's not a lot of people using those yet. 16 gigs of RAM, again, a solid amount. The Quadro RTX 4000 kind of comes out as a sweet spot on the video card side. It's faster than pretty much anything from the previous generation of Quadro cards without being too expensive. A 1 terabyte Samsung SSD, a nice compact chassis, and then a good sized power supply to make sure everything's taken care of there. And just a ballpark from us, that would run around $3,500. And I think probably somewhere in that 3,000 to 4,000 range is what we see as the average for CAD users on their workstation spend. And then moving on to simulation folks, there is a little bit of difference here depending on what sort of simulation stuff you're doing within SolidWorks. If you're using SolidWorks simulation, that particular package is primarily finite element analysis, and that tends to actually only use a few cores but benefit from high clock speed. So very similar to what you'd have in a normal CAD workstation. The same sort of processors that you'd use there do very well, like the Core i9 processors from Intel. The Ryzen stuff's a little bit behind that, but not by much. However, if you're using SolidWorks Flow Simulation, that package, which is primarily CFD, that actually does use more cores very effectively. Not infinitely, you can't throw like 64 cores at it and get great results, but something in the 18 to 24 core range seems to be the sweet spot. So if you're going to be heavily into that, we strongly recommend moving up to one of Intel's Core X models, like the Core i9-10980XE, or something in AMD's Threadripper line, but again, not going crazy. You can get 64 core Threadrippers, but those do not actually end up helping, and in some cases can actually hurt performance, because if you go too high on clock speed, a lot of those processors, or excuse me, too high on core count, a lot of those processors run at a lower clock speed. So something like the 10980XE or AMD's 3960X is a really good spot from the Threadripper side. And honestly, if it ends up being the case that you can't afford something like that, the processors that we recommend for just normal SolidWorks CAD usage aren't all that far behind. You can see in the chart here, they're maybe 20, 25% slower. So it's not a massive loss. You're not losing out, multiple times the performance or something. On the GPU side for simulation, folks, there's not really any particular extra needs. At the moment anyway, everything that I've seen in SolidWorks uses the CPU rather than the GPU for simulations. It's still a good idea, of course, to have an officially certified card. So I would just select it based on the same criteria that we outlined for CAD users. Think about how complex your assemblies are, screen resolution, how many monitors you're going to be using, that sort of thing. And then on the RAM side, this can go up a little bit. It depends a lot on the detail of your simulations. We've found that as you increase mesh size and complexity of what you're testing, the RAM requirements go up. And a nice little tip here is if you're not sure how much you're going to need, overestimate a little bit to be on the safe side, but then you can easily monitor memory usage within Windows. And if you intentionally leave your system when you purchase it with a couple open RAM slots, you can add more later on without having to take out what's in there and waste it or whatnot. So most systems these days, depending on the CPU, will support anywhere from 4 to 8 memory modules. So just populate like half of those up front when you're buying the system, and then that gives you room to expand later on if you find out your simulations need more space without any wasted money. And then some additional considerations. Simulations can take a long time to complete. The ones we run tests on are usually only 10 or 20 minutes at the longest, and sometimes even only a couple minutes. But I know some folks will run things that take hours or days. And if you're doing that, I would strongly consider a system that supports ECC memory. That stands for error checking and correcting. The normal mainstream systems like the Core series and the Ryzen and Threadripper don't necessarily support those. So it sometimes means bumping up into something like a Xeon processor from Intel. But having ECC memory will reduce the risk of a memory error causing a blue screen or some other thing that interrupts your simulation and requires you to redo hours of work. It does cost a little bit more both on the CPU and the memory side. But again, if this is critical stuff, and especially if you have long things, rerunning a 20-minute test, not a huge deal. Rerunning a 2-day test, a big deal. So sometimes it can be worth spending a little bit extra there. And then something interesting that I ran into myself doing some of our benchmarks is Windows automatic sleep timer can be kind of aggressive. In theory, it's there so that if you leave the system unattended, it can go to sleep and save power, which is a nice idea. But sometimes if you're not giving direct keyboard and mouse input, a simulation is just running, Windows will mistake that for being idle, even if the CPU is actually working heavily. So nice little trick if you're doing long simulation stuff and don't want to have that interrupt things, just go to, in Windows 10 at least, go to Systems or Settings, System, Power and Sleep, and then just select Never from the drop-down menu for when it goes automatically to sleep. You can still use it manually, it just won't do it automatically to you. And then kind of an example configuration of what one of these simulation workstations looks like. At Intel, again, Core i9 10980XE or AMD Threadripper 3900X, 32 gigs of RAM. And again, you could do 32 on either of these platforms and still have room to add more memory later. Same RTX 4000 and 1 terabyte SSD we recommended before, but these motherboards usually require a bit bigger, or excuse me, these CPUs require a bigger motherboard, which means a bigger chassis. They also are more power hungry, so a bit bigger power supply. Something like that comes out around the $5,000 mark. And again, that's primarily aimed at SolidWorks flow simulation and CFD stuff. If you're doing exclusively finite element analysis, you can get away with just one of the normal CAD systems instead. And then lastly, for folks doing visualize, it doesn't use the CPU very heavily. It has a mode where it can, kind of a legacy mode where it'll use the CPU for rendering, but the main focus with visualize is using the video cards to do the heavy lifting instead. So the primary emphasis is actually on getting a CPU and motherboard that have a lot of PCI Express lanes so you can put in multiple video cards. So that generally bumps you up into something like an Intel Core X or Xeon W processor, or potentially an AMD Threadripper. Those higher end desktop CPUs tend to have more PCI Express lanes, and PCI Express is what modern video cards use to connect to the system. And so if you're going to have 2, 3, 4 video cards in the system, you want to have a lot of lanes available so the processor can talk to the video cards effectively. And again, if you don't have a compatible GPU for whatever reason, Visualize will fall back on using the CPU, but that's going to be a lot slower and just scale based on the core count, kind of like PhotoView 360 that I mentioned earlier. So assuming you're going down the GPU route with Visualize, the main driver of performance is just going to be the video cards, and it scales performance up with both the speed of the individual card and the number of cards. You can see that there on those charts, going all the way from a fairly high-end Titan video card down to a mid-range GeForce on the left. And it's slower the further down you go on the video card line, but also going from 4 to 3 to 2 to 1 video cards. On the right-hand side, again, you can see it scales almost linearly with the number of cards. So that's good news because it means you can stack a lot of mid-range cards if you want to keep the price down a little bit, or you can stack several high-end cards if you're looking to just max out speed. I should also note the latest version of Visualize 2020, has added in support for RTX technology, which is an NVIDIA thing. I don't remember if it stands for anything particular in terms of an acronym, but it's basically dedicated ray tracing hardware on the GPU itself. And that dramatically speeds up rendering like this, which is usually ray or path tracing that's going on. So definitely, if you're going to be using Visualize 2020 and you're getting a new system, make sure you are getting an RTX compatible card. And I bring that up because some of the lower end Quadros still use the older generation of technology and aren't RTX, and that's also true on the GeForce side. With both of those, though, they make it real easy. RTX will be in the model name if it's supported. And you might have also noticed there I mentioned GeForce cards, and we showed GeForce cards on the slide before, because for Visualize, you don't necessarily need a Quadro card. There are some advantages. Quadro cards tend to have more video memory, more onboard RAM on the card, which can support larger, more complex scenes. So if you're rendering something really massive, you might want Quadros anyway. But for most of the folks out there, GeForce cards will work just as well, and they cost a lot less. In terms of RAM, there's, again, not a whole lot of need here. With Visualize specifically, all they recommend is 16 gigs of memory. And again, that's basically the same thing as the CAD situation. But again, keep in mind other programs you might be using. It is also worth calling out, though, Visualize isn't the only rendering option out there. There are others, V-Ray and other applications that can be used for rendering too. And if you kind of want to explore that in the GPU rendering space, some of those other programs do have heavier RAM requirements from the system. A lot of them will want the system to have as much or more memory than the total number of video cards in the system. So if you had, say, 4 cards that are 12 gigs of memory each, that's 48 gigs. You'd want at least 48, probably more like 64 in the system if you're planning on going down the route of playing with those other applications. If you're just doing visualize, 16 should be good. And then some additional considerations that are specific to a system like this. Multiple video cards means you're going to need a fairly sizable tower or possibly a rack mount chassis. And it also makes cooling a big concern. This should be taken care of for you if you're buying a system from someone, but if you're into putting one together yourself, or if you're looking to get one and then expand and add more on later, it's important to make sure you get video cards that'll exhaust the heat out the back of the system. A lot of them these days are designed to just blow around heat inside the computer instead, and that's fine if there's only one card. But when you've got 2, 3, 4 cards, you can be talking about 1,000 watts of heat being pumped back into the system instead of out, and that ends up heating up everything else, including the other video cards. Definitely a no good thing there. And it is also just worth knowing that more video cards means more fans and more heat, which no matter how the heat's being dealt with will mean increased amounts of noise. So you're going to want to keep that in mind. You probably don't want it next to your desk if it's going to be doing heavy rendering all day. It'll be a little bit noisier than you might like otherwise. So having it in an isolated location can be helpful. And that actually goes back to something that was mentioned earlier. If you're going to be doing a lot of this rendering stuff, you don't necessarily have to do it on your workstation. You can have a CAD workstation and then throw this off over your network. And the same can actually be done with some of the simulation work too. So just something to keep in mind that it doesn't have to be something you bundle all into one computer. And then last thing, the power supply is also very important for such a high wattage system. If you're going to, especially if you're going to be adding to it later on, say you want to start with just 1 or 2 video cards and add more as you need them, you want to make sure that up front you get a power supply that will handle as many things as you're planning on putting in there. Modern GPUs, the high-end ones, can easily be 200 to 300 watts of power each. So you often need something in the neighborhood of like a 1,600 watt power supply for a whole system with 4 of those in it. So just make sure you get that from the get-go. And then just an example of what a configuration like this could look like. An Intel Xeon W, those have I think it's something in the neighborhood of like 48 PCI Express lanes, so quite a bit for running multiple video cards. 64 gigs of RAM, again, this is sort of optimized for V-Ray, or for at least enabling use of that. 4 RTX 2080 Ti cards, the top end of the GeForce line. To go above that, you pretty much have to go up to a Quadro, and then those get quite a bit more expensive. So if you don't need a ton of VRAM, if you're not doing massive scenes with your rendering, these are kind of the sweet spot. And then a 1 terabyte SSD, a much bigger tower chassis, 1,600 watt power supply, that runs something around $10,000. And again, you can also do those in rack mount configurations and whatnot if you want to put it off in a server room somewhere in your facility and just do it remotely instead. So hopefully that gives you kind of a rundown of the hardware that we recommend based on our testing. I'll go ahead and stop this so you can go back over to it.
Excellent. Perfect. Thank you very much, William. Very informative. The thing I like most about that, tons of data to support all the talking points that you have there. You know, you guys are involved in all kinds of testing for each of those applications. Really interesting to hear about it. I appreciate you sharing some of your experience and what you guys offer there at Puget.
You're very welcome.
All right, so to close things out here, we talked about a couple of primary things for today. You're going to consider what software tools you need, and then obviously the hardware tools to go along with it. So ultimately, what do we want you guys to take away from this? How do you find your best path forward to get the best results you can with the right combination? That really comes down to looking to your partners for advice. Quest is here to help you guys with questions on the software side of things. We've got some insight on the hardware recommendations, obviously, since we work directly with SolidWorks. But our partners like Puget are going to be the guys to provide those systems for you and make sure that you can hit the ground running. So if you do ever have questions about it, feel free to contact either one of us, either at Quest or Puget. We'll definitely steer you in the right direction. So hopefully it was useful for you guys today to get into some of the more commonly asked questions about hardware and software combinations. So I will leave the webinar open for just a little bit. If any of you guys have questions that you'd like to type into the chat section, you can go ahead and do that. I'll take those as they come in, or let William address them if they're more geared towards him. Other than that, we appreciate you guys sticking with us for another coffee break. It was nice to have you. Hopefully you're enjoying the series, and hopefully you get to join us for the next one. And William, thanks again for participating. It was a lot of fun to put it together with you.
My pleasure. Thank you for having me on.
Let's see if we get any questions coming in here.
I always wonder if no questions means I answered everything well or I gave everyone too much information and overloaded them.
Could be either one. We'll find out. I'll maybe leave that open for another minute or so. Maybe it's just a really long question that takes a while to type.
Could be. I see a little hand raise thing. I'm not sure
Yeah, it looks like a hand went up. Maybe
exactly.
that means there's a question being typed in. So I'll give it another minute. Feel free to type in there in the chat section if you guys would like to do that, or the questions pane.
Yeah. And I might as well note all the charts and stuff there were all taken from articles on our website. So if folks have questions that maybe they're not thinking of now or something comes up later on, you're welcome to check that out, pugetsystems.com. There's a section at the top where you can go to articles, search through. You can just grab SolidWorks stuff through the little filter on the left if you want. Peruse the stuff there, and then feel free to ask questions in the comments on any of the articles as well. That's probably the easiest way to get a hold of me or one of the other guys here on the labs team.
Very good.
Oh,
Looks like there is some question
yeah.
coming in now, so curious if you've ever played around with overclocking much. What are your thoughts on
Yes.
that, William?
And actually, I think we have an article, it's a little dated now, a few years ago, but specifically on SolidWorks and overclocking, I believe, because that's something I know some other system builders emphasize. What we found is it does increase performance very slightly. One of the reasons it's not a huge benefit is modern processors actually have turbo features built in that are effectively on the fly overclocking. So you'll even see it on a lot of Intel processors. They'll list base clock speed and then a turbo speed. And the base is kind of it'll run at this if you're not doing anything. And then the turbo speed is usually what one or two cores will run at if you're maxing them out and the rest of the processor is inactive. And then there's kind of a spectrum in there depending on how many cores are active, it'll run at different speeds. And that's effectively an intelligent on the fly overclocking. It's taking into account power draw, temperature, load, and adjusting the clock speed to match. You can force it to go even beyond that, but you're really pushing things, especially with some of the latest processors. They're already running pretty hot under full turbo speeds. And when you go beyond those rated specs, what you're doing, we found, is increasing the risk of stability. I was actually talking with one of the guys in our repair department, and they were looking back at things, and almost all of the processors they've had back in repair where the actual physical processor failed were overclocked systems, because we used to offer that. And so you're putting more power through the processor than it's designed for, and it's going to burn out sooner, or at least there's a chance of that. So in from our standpoint, we don't offer it anymore because of stability and reliability. We figure it's probably okay to 5% slower performance for something that's going to last years longer, plus also have less of a chance of things like blue screening out on you or random errors and whatnot. Both memory speed and CPU clock speed are two of the places where we see the most increase in errors just running applications. If things are being pushed a little too far and something goes wrong and it all crashes, you may have just wasted hours of work for a few minutes of savings.
Hmm. Yeah, I'm a big fan of the sort of on-demand overclocking, like you said. I'm on a ninth gen Core i9 right now, and I've
Nice.
seen some significant benefits just running simulations and CFD and so forth. It's great technology, and I think to kind of go back to what you were saying about risk of failure and stuff like that, it makes me think of, a top fuel dragster is not built for longevity, right? You're going to get some huge benefit for the short run, but maybe not so good in the long term.
Yeah. Looks like Ted also is asking about flow simulation. Um, I don't know if that's a recent change or not. We'd been testing both simulation and flow simulation for a few years, and then added actually with some help from someone there at SolidWorks. I don't know if he still works there or not, but someone that was actually working there reached out and provided some larger simulations than anything we had access to for testing. It was specifically some flow simulation stuff, and that's where we saw a lot of benefit from some of those higher core count processors.
Hmm.
Um, and it's, I think,
I do
yeah,
recall some changes a couple years back. I don't remember the specifics on it, but I do recall in some of the what's new material, some of the calculation related changes for flow were to support multi-core, I believe. I'd have to
yeah,
see if I can dig up an article on that, but I seem to remember something like that.
yeah. That might have even been the occasion for why he reached out to us to provide some bigger simulation stuff. I think was he wanted to see with more hardware or more variety of hardware than they had access to, what sort of
Right.
benefits were, especially as mesh sizes scaled up.
Hmm.
Um, So yeah, I do think that's probably a more recent thing. Honestly, the trend toward multi-threading on the CPU side and the trend toward using video cards for stuff outside of traditional just graphics display, those are both fairly recent trends in the last, probably really taken off in the last 5 years.
Sure. Very good. I don't see any other questions at this point, so I think we will close it down. It looks like questions are answered, so very good. All right, if you think of anything else that you'd love to reach out and find more information on, please do so. Support at qintegration.com is your best route to go for Quest, and I think William mentioned their website as well, pugetsystems.com.
Yep.
Jump in and ask for help where you need it.
Yeah.
William, thanks again. Appreciate it, and enjoy the rest of your week.
You too. Thanks.
Take care.